I'm Chinyu Chen from University of Michigan. Today, I'm going to present our project, Keep Others from Peeking at Your Mobile Device Screen. So I believe everyone here has the experience in using his mobile device in public area. Actually, maybe you are doing this right now. And you may notice that a person is peeking at others' device screen, or doing this action yourself. This kind of action is called shoulder surfing. Even though people will take actions when they notice if others are looking at your device screen, researchers have shown that people usually do not know that actually somebody is peeking at your device, with only 7% of shoulder surfing events are noticed by the user. And there are two fundamental requirements and challenges to develop a good privacy protection scheme. First, how to display and protect the information at the same time without blocking the information altogether from the user. Second, how to provide protection guarantee. There have been multiple solutions proposed to solve this problem. They focus on protecting either authentication process or general information, including text and images. When we look at the functionalities, authentication approaches is able to achieve the features required, but they can only be used for protecting authentication process. On the other hand, for the approaches that aim at protecting general information, they can only achieve partial desired features. And the most popular method users use to protect their privacy is to apply a privacy film on their mobile devices. Even though they can provide good protection when the viewing angle of the shoulder surfer is larger than the user. However, privacy film provides little to no protection when shoulder surfers are viewing the device close to the viewing angle of the user. Therefore, in this research, we want to propose a privacy protection scheme that can achieve both features, but without the help of additional hardware. In this project, we consider casual shoulder surfers without professional equipment. That is, a shoulder surfer directly peeks at user's device or uses a smartphone camera to see the information. The goal of our system is to prevent any person to obtain the information if his or her viewing distance is larger than the user by dm, where dm is the protection range margin, which is a design parameter. And our solution to the two challenges here is to utilize grid-based info presentation. So the fundamental concept of our system, HideScreen, is to utilize grids to present the information to be protected. When the user views the grids within a designed distance, he will see the grid pattern. However, if the shoulder surfer views the grid patterns from far away, he will only see a single color block. This protection is based on the fact that if we increase the viewing distance of the same pattern, it is equivalent to increase the perceived spatial frequency. And human eyes or any other optical system have their limitation of resolving patterns. This limitation can be described as a cutoff frequency and can be used to calculate the cutoff distance Dmax of the target pattern. And therefore, given a pattern to be displayed, the maximum visible distance Dmax is also determined for each type of system used to perceive the pattern. Therefore, given a pattern to be displayed, if we view it within the visible distance Dmax, the optical system will be able to resolve the pattern like this. Otherwise, the optical system can only perceive the mixture of the pattern. If we want to display some information using grid patterns, we can use it with a background color equal to the average color of the bright and dark components of the grids. So the information will blend into the background when viewed from far distance. As you may notice, because every screen has different display characteristics, So the screen needs to be calibrated once before applying HideScreen. So given the required maximum viewing distance, Dmax, and corresponding viewing angle, phi, and combined with the minimum resolval angle, theta min, of the optical system we're using, the grid size L can be determined. So to display or protected information, HideScreen will first determine the viewing distance of the user, du. Then HideScreen will determine the required maximum visible distance, Dmax, equals to du plus dm. And finally, it generates the protected information based on Dmax and limit the viewing range of the user to the blue circle area shown here. So now we have introduced the basic idea of HideScreen. We are going to introduce how HideScreen can generate the protected information. And Hide-Image is the name of our image protection scheme. Suppose we want to show this figure of me to the user. Hide-Image will first divide the pixels in a figure into several levels according to their grayscale value. Then it will replace the pixels in each level with different grids with the same average color, but with different bright and dark components. And finally, Hide-Image combines the levels together and generates the final protected image. Here we show the photos of protected image taken by a smartphone camera. They are taken within the designed visible range and outside of the visible range. Even though we can use the same approach we just talked about to protect text, but however, there are some challenges related to the readability of the protected text. Because texts are generally smaller than image when displayed on a screen, it is sometimes very hard for users to recognize them. It is good in terms for protection, but not good for user experiences. So to address this issue, we developed HideText specifically for text protection. First, we treat the text information as a binary image and generate basic protected texts. Then HideText will enhance the readability of the text by injecting 3 layers of boundaries with different color levels. By doing so, HideScreen not only injects the low-frequency components that can enhance the readability of the information, but also injects the high-frequency components that can neutralize the effect of low-frequency components that can be easily seen from far away. HideText then combines the basic protection and edge enhancement to generate the final protected texts. We have recruited 20 people from our campus to evaluate the protection performance of HideScreen. And the results have shown that HideScreen can provide very high protection rate with only less than 4% of shoulder surface recognition rate. At the meantime, the user can have close to 100% recognition rate. That indicates that HideScreen can achieve our design goal that users are able to read the information while the shoulder surface cannot. And furthermore, the recognition rate for the shoulder surface with binoculars are close to 0% because of the mismatch between the visible distance and binoculars focus range. We also performed use case study by implementing 3 applications with HideScreen support, including account login, PIN entering, and messaging. And the results have shown that HideScreen can provide OK to excellent objective user experience rating, and more than 70% of the participants indicate that they will use apps with HideScreen support frequently. So in conclusion, we have developed a set of information protection scheme called HideScreen for mobile device users in public area. And the results have shown that HideScreen is able to achieve both good protection rate and good user experience. And we have another scheme called Select Image for protection of the lossless image, and you can refer it in our paper. Thank you very much. I'm open to any question.